There are many models to represent where electrons are around the atom. So we've talked about electron configurations and orbital diagrams and PES diagrams, and now here we come to quantum numbers. So quantum numbers are not going to be tested directly on the AP exam, but it is considered prior knowledge. So if the prompt says something like n equals 1, you should know that n is the principal quantum number. So you should be familiar with these quantum numbers. This is a quick tutorial on how to do quantum numbers. So Schrodinger's wave equation used four numbers to predict where those electrons would be. And these numbers tell four things. They tell the distance from the nucleus, they tell the shape from the electron cloud, they tell the position in space, so along the X, Y, or Z axis, and they also tell the spin. And the spin for an electron could be up or it could be down. And we looked at drawing an electron as an arrow in orbital diagrams. And this just continues forward and just assigns a number code to that. The first quantum number is called the principal quantum number, and it is represented by an N. So this tells the energy level or the cloud size or how far it is from the nucleus. So if I have N equals 1, then that is going to be the first orbital that's closest to the nucleus. And if I have N equals 2, then that's the next closest one, and then N equals 3. And it tells the cloud size. So an N equals 3 cloud would be a lot bigger than an N equals 1 cloud. The sublevel or the second quantum number is given the letter L. It's kind of a cursive looking L, and it's a code. So S is 0. Often with quantum numbers, we start with a 0. So S is 0, P is 1, D is 2, F is 3. You can do this little formula to figure out how many sublevels there are per energy level, or you could just use your periodic table and count them. But there's a little code here. So the number of sublevels that you can have for a particular energy level would be n minus 1. We have next the direction of the cloud. So this would be m sub L. So it's also called the magnetic quantum number. Really what it's telling you is it's the orientation of the cloud in space. So with X, Y, or Z, around the X, Y, or Z axis with the nucleus right at the origin. So we have an S cloud is just a spherical cloud, and then there's three p orbitals. The first one we can describe as p sub x, so that means it's around the x axis, and the middle one p sub y, and then one the p sub z. When it comes to these quantum numbers, the middle orbital is always a 0, and then you count up. And you can either have just a 1 or sometimes it's a plus 1. Either way is accepted. And then you have a minus 1. So that's describing the orientation in space. If you had a d orbital, or a d sublevel, I should say, here's all my d orbitals. Again, the middle one is going to be a 0, and then you count up, and then you count down. So you have some negative numbers. So what this is saying, if I have an electron in that first orbital, then the code would be it's a minus 2. It's that d orbital. And then the last one is your m sub s. This is your spin. And again, we looked at this with orbital diagrams. If it's up, if the quantum number would be a plus 1/2, and if it's down, it would be a minus 1/2. So let's put this all together. So it's a number code, and there are two pieces of information that you need. You need a electron configuration and an orbital diagram. So if you can sketch those out, then quantum numbers aren't too bad. So let's look at oxygen, and I'm just going to do the last part. So it's 1s2, 2s2, 2p4. So that's the end. And this says the quantum numbers for the last electron in oxygen. You could do a set of quantum numbers for all 8 electrons that are in oxygen, but let's just do the last one because it's easy to describe which one it is. When I look at the last electron, looking at this 2p sublevel, there are 3 orbitals in the 2p sublevel, and let's add our electrons. So our electrons were going to go up, 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 and then the last electron, the one we're interested in, it's down. So that's the one that we are going to be writing the quantum numbers for. Let's do the first number. So the first number, what n is equal to, it is a 2. So for the last electron, 2 is the first number. The next number is going to represent or what cloud that electron is, and it's in a p cloud. And the code for that is 1. So S is 0, P is 1. And then the rest of the numbers come from the orbital diagram. So the first two numbers come from the electron configuration, and the second two numbers you can get from your orbital diagram. So I do need to number out which p cloud I have. So again, the middle one is 0, and then I count up and I count down. And so I am at the -1 orbital. So that's the third number. And then the last is the electron. Is it having an upspin or a downspin? And we're going to say it has a downspin because I can see it. It's going down. So it's a -1/2. So there are my 4 quantum numbers. Now, no two electrons can have the same set of quantum numbers. So this is why when you are doing those orbital diagrams, when you go to put a second electron in, you do not put 2 up arrows in together. So that would mean that you have the same set of quantum numbers. And the Pauli exclusion principle says, no, you can't do that. So every electron gets its own set of 4 quantum numbers. So that's why when you do these orbital diagrams, you got to have the opposite spin if they share the orbital. It's just a way to describe how 2 electrons can share the same space, that one has an upspin and one has a downspin. So if you have your principal energy level n equals 1, or the first row on the periodic table, you can only have an s orbital. So that's just hydrogen and helium. So they are put into an s sublevel, and that ends up being 1 orbital. Principal level 2, however, I can have a 2s and a 2p. And so that gives me 2 sublevels. If I have n equals 3, I can have a 3s, a 3p, and a 3d, but there's no such thing as a 3f, so it stops there. So only 3 sublevels. And then if I have n equals 4, I can have a 4s, a 4p, a 4d, and a 4f. When I look at a p sublevel, we can see that they are split into 3. So recall if you have an s sublevel, because I can put 2 electrons in each orbital, if I have my s sublevel, there's only 1 orbital. So s only has 1 orbital. But when I look at a p, I have on the periodic table, there are 6 electrons that are p electrons. And so I would divide by 2, and that would give me my 3 orbitals. So p always has 3 orbitals, and here they are here. They kind of drew them out. So there's 3 of them. And if you have a d, well, there's 10 electrons on the periodic table, and so I divide by 2, and so I would have 5 orbitals if I had a d. So let's say it's like 3d. And then if I have an f, there's 14 electrons that you can count that are f electrons on the periodic table. So divide by 2, that give me 7. So 7 orbitals. So you can use your periodic table to figure out what these numbers are, how many orbitals there are, how many sublevels there are. There's also a formula you could use to help you to figure out how many electrons there are per energy level. It's 2n squared. So on the first energy level, you really just could count it. On the first row on your periodic table, there's hydrogen and helium. So only 2 electrons. But let's go ahead and use the formula. So 2 times energy level 1 squared, so I would get 2. So you can use this formula to help you figure out quickly how many electrons are on that energy level. On the second energy level, I could just count it. I have 2 s electrons and 6 p electrons, so I should have 8. And when I go and do my math, I should have 8 electrons. The third energy level, I have a 3s, I have a 3p, and don't forget you have a 3d. So you should have 18 electrons. And so I can just put that 3 in there, and I get 18. So I can use the math, or I can use my periodic table. The fourth energy level, you would have a 4s, a 4p, and a 4d. Or you could do the formula 2 4 squared. So I have 4 squared is 16 times 2, so I'd have 32 electrons. So this is just using that formula as a quick way to figure out how many electrons there are, but you also can go through and just count how many sublevels there are. Here's a chart that kind of breaks it down, and so if you're a little confused, maybe you can use this to just help you along to figure out what these quantum numbers are. So I like to write out the electron configuration, but then also the orbital diagram. So for helium, my orbital is my 1s orbital, and then we're doing the last electron, so it'd be up, down. So we're talking about that down electron. So I am on the first energy level, and on the first energy level, the only choice I have is an S sublevel, because that's all there is. There's only an S. There's no such thing as a 1p or a 1d. On the first energy level, there's only an S. So if you have an S as a sublevel, your only choice is to have 0 for your orbital. Because remember, when you start to number your orbitals, you start with 0. So I would label this as 0, but then there's nothing else to count up or count down to. So it's just a 0. So if your second number is a 0, your third number is always a 0. So not often do we say always, but we do say it in this case. I have a down arrow, so that would be a -1/2. And so there's my 4 quantum numbers for helium, the last electron of helium. Let's do another one. So this is aluminum, and my last electron, it is a p electron, and it's right there. So it's an up arrow, and it's in the first orbital. So reading the chart, I have 2 as my energy level, and I do have a p electron, so the code is 1. And then I have that first orbital, so it's a -1/2. Again, the middle one is a 0, and you count up and you count down. And so it is the first one, so I have a -1, and then I have an up arrow, so it'd be a +1/2. So there is my set for the last electron of aluminum.